Hey guys, what's up? Today we are in video 4 part 4 in the series of DSA, and today we are going to discuss about the asymptotic analysis with different notations, asymptotic notations. So let's discuss from first with definitions. So now asymptotic analysis is not perfect, but that's the best way available for analyzing the algorithms. Also in asymptotic analysis we always talk about the input size larger than the constant value as we add the input size, how long does it takes time. Okay, so that we are so after this, the second point, we can say that asymptotic analysis is the mathematical representations or its analysis, mathematical representations and mathematical statements analysis. Means as input size is increased, or repetitions or loop, also we can say iterations of statements, how long, because we know that asymptotic analysis, while analyzing it, we analyze the statement before the execution, before the coding. Okay, so we can say that. So it might be possible that those large inputs are never given to your software, and the algorithms which is asymptotically slower, okay, so always performs better for your particular situations. So you may add with the choosing the best algorithms that is asymptotically slower but faster for your softwares, because we are not talking about the greedy algorithms, we are talking about the dynamical, so we must do that. Okay, now here we are talking about the advantages. Uniform result depends means uniform results depends only on the algorithms, that is the. And disadvantage, if we talk about the disadvantage, maybe estimated or accuracy value, no accurate and precise value, so that is. And let's talk about the time complexity, because in previous video I have already talked about, we are talking about the priori, not the posterior. Okay, so because nowadays we can find the advanced types of hardware, so we don't need we don't face the complexity about the memory, okay, about the space. So we are talking about the time complexity. So how to find the time complexity, that is the problem. So method 1 is say that examine the exact running time. So how to find the exact running time? So analysis, there are two types of analysis we have already discussed, that priori analysis and posteriori analysis. So please, if you have some confusions, you can go with my previous video. So examine the exact running times using the timers and run the operations for the different inputs on the data structures and compares, means repetitions also we can say. And conclusions, in conclusions we can say the one who takes less time is the best performers. Okay, and for the better analysis, compare the data structures on different machines. As I have already told you, this is posterior, so it depends on the machines, it depends on the device, but there might be other problems with the approach. For some input size, as we fill input the size, okay, it's vary into the machines. Therefore, examine the exact running time. We should exact running time means how many times it's iterating loopings. Solution for the time complexity, we can find that points to be noted, like measuring the actual running times. Practically, our running times generally depends on the size of inputs. Obviously, we have already gone through that all. If we have like 1 million, okay, so 1 million shifts, that which will take the 1 million units of time, or maybe, yeah, as you increase the size, okay, may it's depend on the value of the size. So here let's find the functions. Okay, so if you if we are going to note it as function n, so that defined as the time complexity, so we can represent it while instructing this mathematically, while expressing in the mathematically. So let's make a functions. So while functioning, we can find that n is the input value or the size of the input also, we can say. So let's find the function n. So that we can find this. So evaluations of the growth rate, how we can do this all. So please stay tuned so that we can discuss with this all one after another. So while comparing, obviously we have to compare with the constant value as well as. So as well, growth rate, if you are talking about these functions is as growth rate, as the time growth, we can say. So for an example, let's we have here one equations that says that f n square, sorry, is f function. So function n functions here, we have one constant based equation. Suppose one is 5 quadratic or n squares plus 5 7n plus 13. So these are all three different values. Okay, these are three different algorithms also, we can say. So how we can compare with this all? So first let's think that we have n is 1, means size 1. So while operating with that n size, is n equal to 1 size, so running the due times, first let's take about the 5n square. When we talk about the 5n squares, then it takes almost 20%. Okay, so it takes almost 20% of time. And when you take as 7n, so another algorithm, so let's represent by the another algorithm. So we can say, so while executing it, so you can calculate like this. This is the method to calculate actually. So and it's 28. It means it takes time greater than that 5n square or quadratic. And we have constant like as 13, and when we'll talk about this 13 as a constant, so we are talking about these are as a c as constant, and it takes more time, like 52% of time. So but when we will increase the size of n, we are talking about this n size is our size n equal to 1. So when we will increase the size of n, so what will be then after? So we can analyze here. So let's again here we can say that it is the clear observations in this chart. You can find that for the larger value of n, the square terms consumes almost 99% of the time. See here, when it was that 5n square was the least at when n was 1. See here, you can find if when n equals to 1, then you can find the least time consuming here. But when as you increase the size of the n, so here is increased, but constant, as a constant is 13, what we have defined, that is almost 0% time. Okay, so in this way we can analyze. So sometime we can in our daily life also, in real life also, we can find that in like according to our situations we should choose. Okay, in some case, although it's at the first it takes time, but as increase the size, it's reduce the times as well as comparatively, we can say, not exactly comparatively. So sorry, so there is no harm if we can eliminate the rest of the terms as they are not contributing much to the time. Okay, so we can say, we can compare with this all, like we are getting the approximate times, like a complexity, and that we are satisfied with this all result because this approximate result is very near to the actual result. So okay, so furthermore, I would like to go with this. So here is, I have given the notes. Please, you should note down this all. So this approximate measures of the time complexity is called the asymptotic complexity or asymptotic analysis. We are not calculating the exact running time. We are eliminating the unnecessary terms that takes most of the time. So this approximate measures of the time complexity is called asymptotic complexity. So case of algorithm. So while talking about this, so we can go with these different notations. We have all different notations. These all asymptotic analysis are noted by the different notations. So these are very important. Most of the questions are asked in this. So while analyzing, we can find basically these three cases of the complexity. Okay, so one will be the worst case, okay, worst case, and best case, and the average case. So these all different case, basically these all three different cases are noted by with some symbols, with some basic expressions that are called asymptotic notations. Like so worst case is like bad idea. So as we can say, the bad idea, that is noted by as a big O, and then as best, wow, it's the best idea, we can say sometimes. And average idea means average case, like in moderate, in between the worst. And so this worst case is represented by the big O notation. So please remember that big O notations means, so it's worst case while functioning. So this is the worst case, so it's always is greater than our function. So our functions, our time should be always less than big O notation, less than big O notation, because this is the upper bound. And the best represent this best case is represented by the omega. You can see the symbols omega notations, and another is the theta notations. Okay, so big theta notations. We have like a small O and is small omega, but we don't have a small theta. As we can comparatively, these are only theoretically, like small O and small omega. These are only theoretically. I have not seen till now in real life used. Okay, so let's talk about the big O notations. When we talk about the big O notations, I have already told you, it is the upper bound. It is the growth rate functions that shows the highest levels in worst case. So it gives the upper bound of the function by which we can make sure that the functions will never grow faster than that, faster than the upper bound. So our functions will be always less than big O notations. Okay, so we can notify here, like okay, so here that example we can say that 0, here I have as 0 is less than functions, its function is greater than 0, because while executing it takes time. However, it never comes as a 0, it takes some time. Okay, so but while growing as growth rate, it cannot go more than big O. Okay, so let's by calculating we can see if fn and gn are the two functions, then we can say like fn equals to big O gn. So big O gn, so big O gn is always greater than fn. So if there is existence constant c and n0, such that, so we can find, like, see here, fn or fn function is, or is this growth functions is always less than big O. So as comparatively, if you to prove this, we have to find the constant value. So as constant, if you compare this, while selecting the constant value, we have to we have to find the nearer value to these functions. So okay, so nearer value to this function, so that we can make it true. So for all so n functions, n size is always greater than n0. Obviously it takes time of some while executing the programs. So simply this means that function does not grow faster than gn, because gn is here noted as big O. big O functions. So let's here we can find here our algorithms is fn is our algorithm. So we can say here graphically we can represent so that it will be better. So time rate is y represented by y, and input size is represented by x-axis. So you can find, suppose this is the r functions, and in our case, suppose if you are increasing that growth rate, so it's like this growth rates is always grow as faster that as big, that is the worst case also we can say. So in this case, as when it's crossed, that is the, we can say the threshold, or also we can say its average value, or that is n0. So n0, so here we can say that our functions is always less than our growth rate, our big O notations, when she is constant, when she is constant. So in this way we can calculate. So let's by calculating also we can say, suppose fn is here and gn is here. Suppose fn is n and gn is 2n. So how we can find accordingly? Okay, so suppose here fn, let's see, fn is, so while comparing this, let's constant value is 1 and fn 0 is 1, suppose. Okay, so when we'll calculate its linear methods, so it's represented by as linearly, so it grows linearly if n0 or threshold is also 1 and constant is also 1. But as you increase the constant, I told you while finding the constant value we have to find the nearer value. But for another example, let's suppose here is we have fn is 4n plus 3 and gn is n. So we have to find the constant value, because while comparing that we can say that fn is always less than big O gn. Okay, so big O gn, fn is less than the big O gn. So if while comparing, so we have to compare the time, what should be the c value, we have to find that is the c value. If c value is greater, then we can compare it takes time. Okay, so here constant c value, according to the definitions we know that is fn is less than always is Cgn is a constant value, she means. So I'm going to explain here as all with this. So clearly we can see that 4gn is not equals to n, but we need to find whether they are asymptotically equals or not. So fn equals to, we have given 4n plus 3, so you can find here 4n plus 3 is less than cn. So n as n, let's take, we are going to take as n, so sorry, gn equal to n, so you can represent gn equal to n. Now we have to find the constant value. What could be the constant value? Suppose, okay, so suppose let's take c equals to 5. C equals to 5 is nearer to this value I'm talking, so nearer to this value. So if c equals to 5, then let's compare. When we will compare this this value, so it's obviously you can find satisfy its n is, now this fn is obviously greater than gn as you compare. Okay, suppose if you will write n equal to 1, so n equal to 1 is 4n 7. It is not true, but I told you you have to increase the n size. If you increase the n size like n2, then n3, n4, n5, suppose as in some case, till the some case you can find this is false, but as you increase the size of that, it's in one term, it obviously it will lose. All right, okay, so let's, here also we can find that 3 is less than fn is minus 4n. So as you will compare with this, so you can find n is always here greater than 3. So here you can find as n is greater than 3. So as a constant value, if you go to n, so therefore we can say fn is always less than cgn for all n, as n is always greater than 3, where SC equal to 5 and G equal to 3. So in this way we can compare. So let's talk about the big omega. So big omega notations also is the same. We can say the big omega means is the best case or the least time taken. Okay, so least time taken. So we can find this Fn is always greater than big O. So so we can find here graphically we can represent this all. Suppose this growth rate is always lower. Okay, so always lower than function. So it's a threshold we can find. So in this way we can. So let's this also we can mathematically we will go through. I think it will be better, it will be clear. So if while talking about the according to this our definition, Fn is always greater than Cgn because this is the least time taken or the lower bound also we can say. Suppose here is 5 n square. 5 n square is greater than Cn. So Cn, well if you take as C equal to 5 and n equal to 1, then it's true that we can find this big omega. So please calculate with this. And let's talk about the big theta as well as. So while talking about the big O notations and big O theta, so here it's a theta. Theta is average. I have already told you it's always shows the in average between C2 and C1. All right, so here let's when we talk about the mathematically calculate this all in one slide. So while talking about C, Fn equal to 3n plus 2 and Gn equal to n. When we're comparing with this all, so you can find this C1. Let's talk about this. C1 is the big omega. So big omega. So C1 is the big omega because big omega yes, C1 is the big omega. So big omega is the least case. So we can say this always less than the functions, So here C1 equals to 1 and n is greater than 1. So obviously if you talk about the C1, C equal to 1, then it's always greater than 1. So in this you can say it is true case. But for the uppercase says that always C2 is that Gn is always greater than function. So here you can find this also case. So if you'll compare it will be C2 equal to 5. When you take about C2 equal to 5, then you can find this also the true condition. So in this way theta is average also. Theta while representing theta we can say that Gn is always less than functions, but C2 Gn is always greater than functions. So C1 greater is less and Fn, then Fn, and then C2 is greater than Gn. So you can compare with this. So the finally here random access machines is there. Random access machines is abstract machines that just imaginary notation that also we can say this is based on the prior post rear functions. So RAM is this and here you can go with this all definitions. Please go through this, it's only simple. We can find this is very simple way it's explained. I think you can understand with this graph as well as. So as a processor, if you increase the processor, it's depend on the machines. All right, so thank you this much for in this video. So